welcome to the dynamics tutorials. So in this case we have a slender rod that's resting against a smooth surface here at A and B. It's initially starting from a 45-degree angle. Top of the rod is 1 meter over. The edge of the rod here at B is 1 meter over. And so we want to find out the angular velocity of the rod in the instant before it slides all the way down and strikes the ground. We want to find that angular velocity, and the rod is going to be starting from rest. So let's draw our free body diagrams. So here's our free body diagram for our first position. So we've got our normal force at A, we've got our normal force at B, and then we've got the weight and the center of gravity of the rod. There's no friction because we're assuming that it's a smooth frictionless surface at both A and B. Then let's draw a free body diagram just before it hits the ground at C. So we've got our normal force at B, we've got our normal force at A, and we've got the weight. Thinking about these normal forces, they're always perpendicular to the direction that the object is being displaced. And so the normal forces in A and in B can't do any work on the object. The only thing that can do work is this weight W. Coming over here, let's go ahead and also draw a velocity diagram and see if we can find an instantaneous center of zero velocity. This rod's undergoing general plane motion, and so it would be easiest if we could find the instantaneous center. That would make the analysis a little bit easier when we apply conservation of energy. So the end of the rod here is going down in the instant before it strikes. The edge of the rod here is going out in the instant where it strikes. And so we construct a perpendicular here to VB, that's this red line, and then we construct a perpendicular to VA, that's this red line. Where the two red lines meet is our instantaneous center. So strangely enough, at B, the velocity at B winds up being 0 in that second. So if you think about this kind of motion, it's starting here and it's falling. A is moving, but B is temporarily stopped here as it's going. If it was able to continue going, if it didn't hit the floor, A would then continue going down here and then B would start moving in. So think about how A is moving out, stopping, and then it would be moving back in if A was able to go through the floor. And so that's why this velocity at B is 0 here, and that's why that makes sense that that is an IC. Since we've got the IC here, the kinetic energy over here will just be our 1/2 IIC times omega squared, where omega is our angular velocity. So let's calculate that moment of inertia about that instantaneous center. We can get the length of the bar is the 1 meter squared plus the 1 meter squared, take a square root. We get the 1.414 meters. And then our moment of inertia at the instantaneous center, the formula in the back of the book would be 1/3 ml squared, about the end, not about the center of gravity, but about the end. So then we'll plug all that in and we'll get 5 kilogram meter squared for the IIC. And then here's our conservation of energy formula. So our kinetic energy initial plus our initial potential energy is equal to our final kinetic energy plus our final potential energy. So here we have an initial kinetic energy of 0. Our potential energy is only just due to the weight moving about in y. So our potential energy for 1 would be our weight times our y position of the center of gravity at 1. Our final kinetic energy here would be our 1/2 the moment of inertia times our omega 2 squared. And then our final potential energy would be 0 because we're down here on the floor. So then plugging in our numbers, we get our 5 kilograms times 9.81 for our weight. And then our center of gravity here is halfway up. So instead of being the full 1 meter, it's going to be half of that, so 0.5 meters. And that's equal to our 1/2 of our IIC times our omega 2 squared. We can solve for omega 2 squared, and then don't forget to take the square root, and that'll give you the 3.13 radians per second. Thanks for watching.